discussions we have afterwards.
Fantastic. Yeah, thank you for having me. Unfortunately, yeah, I'm only here for the day, so look forward to chatting with people afterwards. Yeah, I'm going to talk about this paper that my co-authors and I put out recently, Classical and Quantum Algorithms for Characters of the Symmetric Group. And this is joint work with Sergey and Wojciech at IBM and also David Gossett at Waterloo. Maybe spoiler, these are very hard problems. I'm not going to give you an efficient algorithm for these. That would be pretty revolutionary.
We will forgive you.
Yeah. Oh, also, please feel free to ask questions at any point. Some of the content may be a little technical, and we may skip over bits time dependent. So please let me know if anything is unclear. Okay, cool. This seems okay, cool. Okay, just a short bio about myself. I'm now in my 5th year at UIUC Electrical and Computer Engineering. My advisors are Chetan Bar. I've done a lot of different flavors of quantum info research in grad school. A good bit of things that fall generally under some sort of quantum learning theory, also entanglement theory and representation theory, as you would probably guess from the title of this talk. Before that, I was more of an actual physicist and spent a lot of time working in labs. I clearly don't do that anymore. So something changed.
That's okay.
Okay. So again, this talk, I'll focus on a few of our results here. The first being we'll give a tensor network algorithm for computing characters of the symmetric group. And then on the flip side, we'll also show that there are efficient quantum algorithms to prepare the corresponding tensor network states. And then more generally, we'll talk about something related to simulating certain types of distributions, sampling from certain types of distributions. And there's a few reasons we're interested in this. Well, I mean, the first one really is that representation theory, as I imagine I don't have to convince you, is very important in physics and also shows up a lot in quantum information as well. And then also we have access to certain operations that are representation theoretic that seem very difficult to perform classically. So we have a very nice protocol from Beals from a while ago to perform a quantum Fourier transform over the symmetric group. People for a while have been looking at this with the hopes of solving, like graph isomorphism, for example. Seems like maybe it didn't quite get you there, but still it's something that it seems like would be very difficult to do classically. And we hope that maybe you could leverage this to get some sort of quantum advantage, right?
But graph isomorphism is not NP hard, right? So that's kind of considered one of the easy, right?
Sure, yes. Yeah, I mean, good number of computer scientists think it's polynomial time classically.
Yeah.
Anyways, right? But people have been hoping that you could use this for a while to solve graph isomorphism because you can frame it.
That's right, but okay, yeah, indeed, I'm aware of that development, but I'm not quite sure what came out of this. But
I think it just kind of doesn't work in the end, unfortunately. Was the conclusion, or none of the more obvious things work, something like that. Anyways, okay. And then just further, it's a fundamental problem in group theory, and hopefully I don't have to motivate looking into problems of theoretical interest. Okay. So now talk a little bit about the connection between spin chains and characters, which is really what we're going to be leveraging in this work to get tensor network algorithms. Okay. So we'll start with the spin chain. I imagine this is very familiar to basically everyone. So maybe we
would never underestimate the happiness of people who see things that they know.
Yes. Anyways, I imagine this is quite familiar to people. So for our purposes, this will be some one-dimensional, assortment of spin 1/2 particles, the qubits, And there was a very nice paper from Kuchino and Prakash that came out. Oh, I forget the exact date, but sometime last year, where they looked at sort of what spin chains encode in their behavior. And I very much encourage you to read this paper. It's very, very good. And sort of part of our motivation or part of our inspiration in this paper. And they prove that spin chains can encode several different objects from representation theory of the symmetric group. They prove that they can encode characters of the symmetric group, also Koska numbers, as well as Littlewood-Richardson coefficients. All these things appear in the representation theory of the symmetric group. And they prove this all using some connections to symmetric polynomials and applying symmetric polynomials on spin chains. And so one of the things that we're going to do in this paper is we're going to use this link to construct MPS algorithms. So we're going to take this mapping on the spin chains, and then we're going to write it down as a nice-ish tensor network, and then we're going to contract that tensor network. It's basically the high-level view here. Right. And in particular, we're going to think about the spin chains in the following form. So this is going to be based off of like second quantization. So we're going to work with in theory, countably infinite spin chain. For all the tensor network purposes, and actually for all the encoding purposes, it turns out you can clip this chain, which is probably pretty important for actually being able to simulate it.
Also important for the fermions, right? For the parity sector, maybe.
Yeah. So, well, okay, more on that in a second. So, maybe this chain here represents some string of integers, right? So maybe you start your indexing there at 0 or something like that, and this encodes some chain of integers. And then, of course, also we're going to be interested in applying creation and annihilation operators. I imagine these are probably familiar with people, but maybe we'll define them nevertheless. Creation is going to take an unoccupied site, occupy it. Annihilation is going to do the opposite, right? Yeah.
So you look at like you have one state that is all up, and then you only look at states that have finite in.
Yes.
Okay.
Yeah. Everything's gonna be finitely many. And then you also use some sign terms here as well. But yeah. So what Krzyzhenko and Prakash show is that basically you can, using these annihilation and creation operators, encode symmetric polynomials into the spin chain. And the way that they do this for characters at least is something called a kernel operator, which basically just causes sites to flip through the chain. So if you look at this here, this is annihilating at index I and then creating at index I plus L. So
in the spin picture, that would be like in the pre-image of the Jordan Wigner would be a Z string in the middle.
Yes.
Right? Okay.
Yeah. So exactly in this mapping here, because this is for Jordan Wigner, there is a Z string. Yeah, for this explicitly. And we'll see that very explicitly when we have a tensor network for this. Yeah, exactly.
So are you considering an Hamiltonian in qubits, and you are mapping to fermions through Jordan Wigner?
I guess we're not necessarily so much imposing a Hamiltonian what we're doing here. That's part of the motivation in the Krzyzhenko Prakash paper. I forget exactly which model it is. It's one of the simple ones they show us in the beginning. It's like, I think that XX.
Okay, so you are considering an XX Hamiltonian like a translation invariant or like a nearest neighbor?
Nearest neighbor.
Nearest neighbor, yeah. And disorder with disorder. Not translation invariant.
No, this should not be translation.
And right. 1D interaction or also next to next?
It's just next. Everything would just be next to next.
So nearest neighbor plus next to nearest.
Oh, no, just nearest neighbor.
Okay.
Yeah. Yeah.
I mean, as I said, you don't want to impose an Hamiltonian.
Yeah, that part is sort of less important for us.
Phrasing the language of reasoning about fermions in the language of spins.
Yes. Well, it's more just that you can represent all these things for representation, or take all these things for representation theory and map them into like fermionic systems, basically. So that the Hamiltonian part is a little less important for having a specific Hamiltonian in mind is kind of less important for our purposes.
Like this is more like the dictionary for if you speak about like fermionic things, think about this in terms of spins. Or think about it like this in terms of spins.
Sure, yes. I mean, again, the idea is more just that we want to take these things from representation theory and then embed them into a fermionic system.
Yeah.
And we're really, at least for the purposes of our paper, I don't think the word Hamiltonian's in there once, so. Not,
We sympathize.
yeah, not really the main focus, but anyways, okay, so they take these current operators, which are really just, jumping around this chain. So let's maybe look at like a very simple example of this. So just applying J1, which would just be jumping one side. It's just going to take these two and flip them. That's all I'll do, right? Because all the other sides are unoccupied, right? So it's not going to have any impact on this. Okay, and as I've been saying, what they end up showing in their paper is that basically you can just clip this chain to a finite number of sites, 2n actually, and you can begin with a fixed input state, and then repeated application of these operators will encode all the characters of the symmetric group. And they generalize this to more than that, and I'll get in more detail on this. I wanted to maybe put the cart before the horse a little bit, because next time we talk about representation theory for a second before being able to formally state any of this. But the idea is basically just that you're able to truncate this chain, and then by applying these operators, you can encode the characters of the symmetric group. And perhaps before I talk about representation theory for a second, let me ask if there's any more questions before going on. Maybe I should have the time.
That's wonderful. By the way, maybe a comment from my side, because it's great that we have questions, but you're also the boss of your talk. I mean, it might be, when you talk about representation theory, spin chains, symmetric groups, I mean, there could be many questions that doesn't.
No, I mean,
you also have the right to continue.
I mean, we have to 3 PM, then this room is.
Yeah, that's right.
Well, hopefully William will go.
I'm joking. I'm just saying, you're the boss.
Okay, so we're gonna take a little bit of an interlude then into representation theory. I'm going to try to make this as bare bones as possible. So I'll just try to define everything that's basically absolutely necessary and maybe no less. And hopefully that will work. Okay, what's the basic idea? Well, the basic idea is that for representation theory, you want to take some group. You want to take homomorphism, which is the row here, and then a vector space V, and then you want to map into the unitary group on that vector space. So you want to take some more arbitrary notion of a group, and you want to map it to something concrete, basically a matrix that acts on a certain vector space, right? So maybe some examples are helpful. Okay, any group emits a representation on a one-dimensional vector space. We'll just identify it with the complex numbers, right? Where you just map everything to one, right? Multiplicatively. So this is clearly a representation because, this is clearly a homomorphism, because if you multiply two of these things together, you always just get one again, and people call this the trivial representation. So this works for any group. It's, as the name would suggest, sort of not that interesting, but yes. it always exists. And then, okay, what's another representation? Well, you can take the group itself to be the unitary group, and then take the representation space to just be the d-dimensional vector space, say if you're looking at d-dimensional unitaries. And then the representation is just how you would sort of canonically think about those matrices, right? It's just acting on the vector space in sort of the defining way. But that is an example of representation, because you can define other ways of representing that unitary group on different vector spaces. I said this before, but this comes up a lot in physics as well as chemistry. Maybe I won't belabor that point too much. Okay. And the next notion that's going to be very important for us is to have an irreducible representation. These are sort of the building blocks from which you build any representation of a group. So, okay, we need just a couple concepts for this. The first is that of a subrepresentation. So you take a vector subspace and require that it's fixed under the action of the group, under this homomorphism. So that restricting the homomorphism to just W is also representation of the group. So that's a subrepresentation. So, okay, I didn't give an example of that, but maybe one like really easy example of this is just take like, some arbitrary number of copies of this representation here, the trivial representation. So, maybe take K of them or something and just have on each one-dimensional subspace, the group just acts as identity or something like that. Then clearly each of those one-dimensional subspaces is also a subrepresentation. So that would be a pretty simple example. And we'll call a representation irreducible or an irrep if it has no proper subrepresentation. So there's no subspace, no proper subspace that is closed under the action of this group. Okay, so I just mentioned about D-dimensional Hilbert space as a representation of the unitary group. Well, it's also an irreducible representation. And a very important result in group theory is that if you have a finite dimensional representation, you can split into a direct sum over your F. So that's why I have this image over here, because basically if you take any finite dimensional representation, it turns out that it's built entirely off of stacking together irreducible representations. So that's why irreducible representations are very central to representation theory. In some sense, studying irreducible representations is really studying every possible representation. So it really suffices just to study those. And there is one other concept that we'll need before we can get back to our paper, which is that of characters. A character is a seemingly pretty straightforward map on representations. So you just take the matrix row G and you take its trace. That's it. That's the character. And it's not hard to see. I'm not going to formally prove it here. It's like 3 steps or something. That the characters are fixed on conjugacy classes. This just follows because of cyclicity, trace, and row being a homomorphism. But anyways, so this is what we call a class function, which means it's constant on conjugacy classes. And these are very important in representation theory, partially because of the following result. And this is maybe not too hard to see just from the direct sum characterization, which is that if you have the character of any representation, it's just the sum of the irreducible characters. And further, you can really say that this uniquely identifies the representation up to isomorphism. If you knew the character of your representation, you would be able to uniquely split into a direct sum of irreducible representation. So these are pretty core to representation theory. And I won't say too much more, but maybe I'll just give an example. People like to put these together, which are called the character tables. So on the top here, we have the conjugacy classes of the symmetric group, which are labeled by partitions. And then on the rows, we have the irreps, which are also labeled by partitions. And these are the values of the characters. So people like to put these together. For S3, it's pretty small, but it spreads pretty quickly. Okay. And okay, so almost done with background before we can get back to our talk, but it would be hard to continue with our paper without defining these things, to be honest. So I imagine people are familiar with the symmetric group, but just in case not, the symmetric group is the group of permutations of n objects. You take n things, and if you're drawing like tensor networks, it would be shuffling around those n incoming wires. It's a very nice way of drawing them out. And what you can prove, but I'm not going to do here, is that all the irreps of the symmetric group are labeled and in correspondence with partitions of n. So what's a partition? A partition is some tuple of non-negative integers that is sorted. You don't necessarily have to make that assumption, but it makes life easier. And also sums to n. So here's a couple simple examples and why it's shown on the prior page for the character table. These are all the possible partitions of 3. You have just 3, then 2 and 1, and then 1, 1. Those are all the ways in partition 3. And then it's nice that it turns out that also all the conjugacy classes can be labeled with the exact same thing, with partitions as well. So for example, let's take this permutation in S6 here. Let's write it in cycle notation. And it's pretty clear from cycle notation why this is true, right? You just read off the number of different types of cycles, and that gives you the conjugacy class that object. So for this one here, it's 3, 2, 1, because you have the 3 cycle of 1, 2, 4, you have the 2 cycle of 3, 5, and then also there's a sort of hidden cycle there of just 6 being back into 6. So that's the cycle type. Okay.
Sorry, what do you say that is clear that also this relation conjugacy class if you only partition of M from this example, or what it's clear?
In general, right, you can write any permutation in cycle notation, right, which is you split up the action of the permutation into distinct cycles, which, just shuffle things like cyclically within this. So this takes like 1 to 2, 2 to 4, 4 to 1. Right? And you can write any permutation in this form. And then if you read off the lengths of those cycles, that's exactly the conjugacy class of that permutation. Because if you conjugate this, it doesn't change the cycles, it just changes what's being shuffled in the cycles. And you can do that sort of arbitrarily, so you can create any other permutation with the same cycle type, that form. So this is, perhaps this is pretty non-trivial, that you can write the EREPs also as partitions, but this just follows very neatly from cycle type determining the conjugacy classes. So then you just sort the cycle type, and that's partition. Okay, one last representation theory slide, I promise. This one's gonna be a little grosser, but that's maybe to serve a point. Okay, so let's take 2 partitions now. This mu representing the conjugacy class that we actually want to compute a character on. And then there's this very famous theorem from, when Frobenius coined this over 100 years ago, that this character is the coefficient of this polynomial in this thing. Where this is, of course, a van der Waals determinant, and this is some product of what we'll call these P mu JZs. So recall that mu is the cycle type of the element of the group G, and lambda is the EREP they want to compute this on. And part of the reason I put this on here is to say, well, these things aren't very nice. These are not very nice to work with. In fact, you can prove that in worst case, these are very, very computationally difficult. You can prove that they're sharply hard to evaluate.
And Z is from which set? Like Z is from which set? Like, is it real, Boolean?
It's sort of arbitrary. It's just as a formal.
Okay.
It doesn't matter. This is just as like a formal, formal expression.
I see.
Okay, maybe the purposes of this talk, think about it as M complex numbers.
Yeah.
Or M values on the unit circle.
Okay.
But it doesn't matter.
So you can also think that Q set is just the generating function. It's
yeah.
Yeah, I see.
So it sort of doesn't matter.
Yeah. Cool.
But okay, so it's very hard to compute these things, as I would hope maybe this sort of a little formidable expression suggests here.
Sorry, is it hard to compute? The statement is that for each point is hard to compute, and what about approximation?
Okay, so for starters, all the characters are integer valued. So if you're able to compute within less than 0.5 error, you would just be able to compute it exactly, which is actually an important point that I'll come back to later when we're actually running
integer linear programming or semi-definite programming, or it might even be of this type, no?
Ooh, I'm not sure how to write it as You may be able to, are also polynomial expressions for the characters, they're just.
The polynomials, and it relax these higher order polynomials like Laplace type to SCPs, but they're still integer values. Maybe it's like a never mind. We can discuss this later.
Sure. But anyways, the takeaway here is that these things are not that pleasant to work with.
Yeah.
Sorry, but it's not clear that, okay, you say that this polynomial is hard to evaluate in point and also implies that the coefficients are hard to evaluate. I mean,
Yes, I want to translate. Can you say again what is the hard thing here?
The hard thing is evaluating the characters. We know this is computationally very hard in worst case. So actually trying to compute the coefficients of this polynomial is a hard problem.
And that comes from the characters.
Yes, yeah. Because the coefficients of this are embedding the characters, right? So.
And that's from the combinatorial nature, right? Because otherwise it's just building traces, but then you have to say traces over what, and then trouble starts.
Yeah. So, like writing out this polynomial will be a very computationally difficult task. Also, just because this grows very quickly. I mean, that's sort of the underlying motivation here. This is going very, very fast. Okay. So then let's talk about how we embed this into a spin chain. I have some slides about how we actually do this that we'll get to if we have time, but they're maybe a little more technical, so we'll probably skip them for now. So what Krichkino and Prakash prove is that for any n and a permutation of the symmetric group, you clip it to n sites, and then you can encode all the characters of a specific conjugacy class in this state here. This isn't normalized, so it's not a proper problem state, but I may call it a state nonetheless. And what you're doing here is you're starting with a specific reference state, this n spin down 0 or n spin up state. And then you're applying a bunch of current operators. So remember that these were these jumps. And they proved this using some symmetric polynomial theory, which is very, very nice. And showing that these jumps are encoding sort of walks over partitions. And we give a different proof in our paper, which is maybe a bit more physicsy, and it's based off of fermionic second quantization. Again, I have slides on that. I think we'll come back to that maybe if we have time.
One question. Do you exploit any fermionic symmetry in the MPS, like particle number or fermionic parity?
At least parts of our implementation are perhaps a little naive, and I'll get back to that because we think you could probably speed up things a lot.
Right, yeah, I guess so. So if it's just fermions being occupied or empty, you can exploit these symmetries in the numerics.
Yeah, so maybe we'll get back to that in a little bit, because I think you can probably do much better than the runtimes that we saw.
To put this in perspective, I mean, Philip has a very strong background in exploiting symmetries in tensor networks.
Okay, yeah, maybe we should talk about
that. On this, so maybe you should, it might be helpful.
Yeah. Because I'll show you some numerics in a little bit, and then maybe we can talk more about this offline. It'd be interesting to see how.
Yeah. Sure. Yes.
This, yeah. Okay, so let's take a pretty simple example. So let's look at n equals 2, which is just a symmetric group on 2 elements. There's just one non-trivial operator other than identity, or a permutation other than identity in this, right, which is just flipping 2 elements, just swap operator. And let's look at the state that encodes characters here. So it's just linear combination of these operators acting on 1, 1, 0, 0, which is this state here. So again, we've clipped the spin chain now to 4 sites. We'll look at applying this one first. What this is going to do is it's going to jump this occupied site over another occupied site and land over there. And you're going to pick up a sign in the process, right? So you're going to flip these. And then similarly, you're going to jump another site here as well, but there's not a occupied site in the middle, so you don't pick up a sign. It's all clear now?
And the picking up the sign is the mentioned Pauli Z string.
Yes.
On the draw.
Yep. Yep.
Nice animation.
Yeah. Thank you. So then you end up getting this when you apply this current operator. And this does exactly encode the characters of this element of the symmetric group. So there's only two possible irreducible representations for S2. That's just the identity and what's called the sign representation. And the sign representation is just exactly the one where the swap operator is mapped to -1, which is this one here. And that's the trivial representation. There's another one there. So this encodes the characters as we were expecting it.
Can you quickly go back to the general expression for the theorem?
Yep, there you go.
Okay, cool, thanks.
Yeah. And like I said, in their paper, they also give a bunch more other mappings. I mean, they map, just general symmetric functions and all these things, characters and much other constructs of representation theory all linked through the theory of symmetric polynomials. So you can kind of import almost, well, maybe not necessarily almost anything, but you can import a lot of relationships from symmetric polynomial theory directly then onto actions on a spin chain, just because you're able to enact these polynomials basically.
And I suppose that the hardness can be seen in your formalism in the product over the sums, like.
Yeah, so this grows very quickly.
Each of the A dagger A's kind of just moves around some things, but it's essentially all staying phase state. It just changes to a different one. You have the sum and the products, and then you get the particular overlap. Then you need to know like which of all those many terms.
So for now, you've not explained why or if that's an efficient preparation, and presumably it isn't, right?
Oh, it's not, of course not,
because that might come later. Okay.
No, this is very inefficient. Like we have bounds on the bond dimension resulting MPS, of course, but they're not very good. I mean, if this was efficient, this would collapse the polynomial hierarchy, right? So that would be surprising.
Well, just to clarify, what's the X lambda tau, lambda plus tau?
I will not formally define what it is. It's just one of the amplitudes of this state here.
So what is tau?
Yeah.
I probably should cut that out, to be honest. It's a certain fixed partition. Again, actually, I don't want to formally define this. Maybe it would take us.
Okay, but if you tell me there is a fixed partition, that's okay. So there is a way to fix a partition, and then you compute this amplitude, and that's it. And the mu's here are the cycle count of the lambda, no?
Yes.
Okay.
And
no, the mu's are the cycle type of the
lambda
of the G.
Yeah, exactly.
Because then the lambda is coming up in the amplitudes.
Lambda, plus this stuff.
So this state here in its amplitudes encodes all of the, as you fix G, it encodes all of the characters as you let lambda vary. Right. And again, maybe I don't want to formally define this for now. I think I do on another slide, but I'm not sure if we'll get to that. But basically, if you could read off all the amplitudes of this, you would know all the characters.
Amplitudes in the computational basis. So X is a computational basis.
Yes.
You're right.
Yeah.
And the quantum state is efficient preparable because like you can just symmetrize the JL, but the symmetrized part is annihilating the resource state anyways.
The quantum circuit for this is maybe slightly different than just trying to directly apply this, perhaps. It's using the Fourier transform of the symmetric group. I'll talk about that in a little bit. But it's not just directly trying to do this. I mean, that does get us the that's a good time to move on to the tensor network approach, because the tensor network approach is just trying to implement this this evolution with the tensor network. So the sort of base state we're starting off with this n excitations, and then then n unoccupied sites is a matrix product state. I mean, clearly it's really unentangled, so we just have a bond dimension 0 or my view. Then what we're going to do is we're just going to do sort of the obvious thing. We're just going to write out these current operators as matrix product operators, and then we're going to apply this iteratively, right? That's it. So, what we can show is that these current operators are matrix product operators of bond dimension L+2. And here's proof of that. Maybe this takes a second to parse. So I have an example that maybe makes it a little clearer. So let me look at like J2 for a second on like
And
a few sites.
in the L+1 bond, you need to communicate the information through the leg of the MPO, right?
Yes. Yeah. Yeah. It's so you can construct like a chain of increasing indices
I see.
going throughout it.
That reminds me of a discussion I had with Senko. See? No.
Yeah, so that's what's going on here. So you can see it explicitly in this example I gave here, which is that you're starting from 0, and then you're going to 1, and then you're going to 2, and then you're going to 3, and then you're staying at 3. So the idea is you're going to start at 0, you're going to go to 0 to some point, and then you're going to start increasing the numbers here, and you're going to construct like a, you know, L increases of that form. And when you go from 0 to 1, you're going to perform annihilation. When you go from L to L+1, you're going to perform annihilation, and then everything else, or sorry, creation. Then everything else in between, you're going to put a poly-Z on, right? This makes sense?
Makes sense.
So yeah, again, the idea is that you're going to stack a bunch of these together, and you're going to try to then, for more arbitrary L, create like sequences where this is increasing and you're wedging Z's between annihilation and creation operations. So that's exactly what's going on here. I don't have a slide on this, but we also, in our paper, gave a sort of similar construction for computing Koska numbers, which are something that's also important in representation theory of the symmetric group. So you can do something kind of similar.
One question to this slide. Is that a single current operator, or is it the sum of two current operators?
This is a single one. So, you know, you apply these iteratively.
But then I don't see why it's bond dimension 3. It should be bond dimension 1. No?
For which one?
In the spin world, it's bond dimension so and so because of the Z tail.
So here's the, yeah, you have to put all the poly-Z's between the annihilation and creation.
But isn't that just a product of operators, of our local operators? So it's bond dimension 1, I guess.
Yeah.
There's just a product on the single side.
Okay, wait, sorry, I think I misunderstood your question. This is a summation over.
Okay, then it makes sense, yes.
Yeah, this is like the current operator is a summation all over like all these jumps, right? So, sorry, I misunderstood. I thought you asked if this was like a product of different current operators. No, this is encoding like all of them simultaneously, all the like jumps.
I see, yeah.
Of the current operator, right?
Okay, thanks.
So no. This is not just like a single jump, because of course that's like a separate operation, right? It will be very easy. This is encoding all of them as you sum over the chain. Okay. So then we're going to do what you imagine, which is basically just iteratively apply these and then perform truncation. So we're going to start off with this reference state. We're going to iteratively apply the MPO construction of these current operators, and we're going to truncate them. So, you know, we're going to start with this. We're going to apply the current operator and so on. And when I write compress here, I mean sort of the standard thing you would do if you're creating SVD states, right?
So,
huh?
The SVD type, you need look at the relevant subspace.
Yeah, exactly. You just chop off all the small enough singular values. Yeah. So just the standard thing you would do.
Also, like to see this as a quantum circuit would also not help, right? I mean, of course, you can see the MPO as a traced out MPS, and that you can see as a sequential circuit using a quantum circuit. But again, the bond dimension would be high, and that would be like a very inefficient quantum algorithm.
Yeah, I mean, again, the quantum algorithm that we give for this is maybe slightly different. So than just trying to directly apply these things. Yeah, but cool. Okay. So then just one more note on this before I show some numerics. So of course we want this psi G state where you're directly applying these, but we're getting something in the end that isn't exactly that because we're doing this compression, these singular value decompositions. But that's sort of not too much of an issue if the error is not too large. because if you're within 0.5 of the correct value, because you know the characters are integers, always for the symmetric group, then you could just correct it to the right value. So if there's error, but it's not too much error, then it works. And we can also bound the bond dimension. We get this product directly from the MPO construction. So remember that the bond dimension of JL, we gave a construction where that bond dimension is L+2. So then basically you just take the product over all of the different current operators that you apply. So that's a bound on the bond dimension, which is, of course, going to grow very quickly. This cannot be efficient. I mean, like I said before, if this was efficient, they would, collapse the polynomial hierarchy. So we're not expecting that. So here's some numerics.
With gap, whoa.
Yeah, we compared it to some other packages. We compared it to Sage's implementation and also the implementation in Sage through gap. The blue is our implementation, orange is gap, green is Sage, and also this on the right is the bond dimension for the corresponding MPS as well. So maybe I should be a little clear here that the goal here is not to compute a specific character. It's the fact that once we've constructed this matrix product state, we've effectively computed all of the characters as you range over lambda. So our goal here is to really compute all the characters. So this is for a specific numerics here for a specific cycle type. This is partially chosen, because this sort of has a lot of operations, right? So this is cycle type 2 n over 2 times. So you're applying like a linear number of these current operators, which is a lot. So you would expect the MPS operator to maybe not do so well, or the MPS approach to not do so well on these. But we do see in practice that while Sage is maybe a lot faster on smaller instances, seems like our approach starts to scale better eventually. And also when we compare the actual bond dimension to the upper bound we get, we see that it's a pretty stark difference between these two. We can guarantee this, but in practice it's a lot smaller. Yeah.
Yeah. Would you say then that the hardness comes, or the intuition is that there are too many characters, because a single one I can compute the coefficient of this polynomial, not the interventions of. But the point is that there are too many of them. Or
no, because there are certain ones that are hard cases, and if you could compute those, you would collapse the polynomial hierarchy, like a specific one.
So there are even hard ones.
Yes.
Like the specific ones that are known that if you could.
Yes, if you can compute those specific characters, you would you'd be solving a Sharpie hard problem.
For a time.
Yeah.
Wow.
But yep.
No, you were first.
Those characters are of this type of having a large cycle type, or?
Oh, I don't remember. Yes, I don't remember exactly what the construction is, but they are large, a lot of cycles. These seem to be generally sort of the ones that are harder to work with, because for like very short ones, things maybe simplify a bit. I don't remember exactly what it is, but I think if I remember correctly, at least one of the original constructions is something similar to this, where it's like you take something that's like rectangular. Like this is rectangular in the sense that you're stacking 2 a bunch of times. I think it was you take something rectangular, maybe it was 3 actually, n over 3 times 3s. Maybe it was that actually, and you could stack a bunch of them. You could reduce, I think it was like some sort of knapsack problem to computing these. And there's other reductions that have been shown for slightly different variants of this volume.
I mean, I find your runtime scaling is stunning.
It's pretty well.
First of all, it's very impressive how fast your algorithm is. It's really nice. And you also beat gap. But also quite interesting, like how different it is compared to Sage, because gap. I mean, I had David Gross, my former PhD student, also now professor in Cologne. He said that gap is a sign that God exists, because it was so magically powerful that this is possible. But it's a symbolic thing, right? It's not doing it. It does a symbolic group calculation. So it's kind of funny that it's almost the same as your MPS, which is very different in flavor. That Sage is so different. Your MPS approach is so similar to a fully abstract symbolic computation
in some ways.
compared to the sage, which seems completely off. Like, whoa.
But
I wouldn't have, I mean, if this had been the other way around, I would have believed it more.
I mean, okay, maybe there is a caveat here in which that you do maybe, if you want to scale this further, need to be careful about the approximation error.
Oh, yeah,
So these were all with a fixed approximation.
But it's cool.
And like it worked for these, but you know, as you scale and you probably have to change that, and the time complexity is probably going to be a pretty strong function of that.
Yeah.
I mean, on the flip side, I think if you grow n to be, you know, more than like 100 or something, already computing these things is something you would think would be like pretty ungodly. So maybe,
yeah.
But those on the left side, like they are with a certain approximation error, but they are like correct.
yeah, because you can round them.
Yeah, exactly.
Yeah,
So
you can round them. So these are like, you get the correct value
exactly.
here always. Yeah.
So I mean, in that case, I would guess then that if you take into account like the approximation error, then what would change would rather be that the left, like the small n regime, blue bars would become maybe even faster because worse.
Yes, we were taking a much,
worse approximation error would even suffice.
yeah, we were taking much closer approximation than you probably need. I don't remember what we said the actual observed errors were, but they were very small. Like none of the things actually had to be rounded very far. All the errors I think were like order like 10 to the -6 or something before rounding. So you could certainly do better.
Yeah.
I mean, okay, this is also a good point. I know there'd been a question about trying to optimize this. This is very heavily unoptimized. I'm sure you could do much better. This is entirely run in Python. I imagine you could probably also do some sort of like GPU interfacing or something like this, because it's entirely just like tensor operation. This is extremely unoptimized. But even with this being extremely unoptimized, and there's not a ton of tricks we're playing here, it still seems to do better than Sage for like enlargement, which is kind of neat.
Right.
Okay, yeah, questions? Yep.
The runtime to NPS, is this the runtime to get the NPS or the runtime to get the coefficients? Like the
No, this is computing every character. Yeah, no, this is not just creating the NPS. This is computing everything properly. Yeah. Great. Yeah, question?
Okay. So are you sure that these are the correct coefficients? I mean, your algorithm.
Yeah. We're comparing them to Sage. And yeah. So if you believe in the Sage, then these are correct.
I mean,
like I checked some instances for like small n, you know, which I can do by hand, but then for large n, I think you just have to believe that Sage is getting the right answers.
I'm not doubting about your results. I'm just asking if there is a way to check if your number that you get from your algorithm is correct.
No, unless I think the there should not be an efficient way of doing that, I think, unless the polynomial hierarchy collapses.
Okay.
So.
And there is, okay, so
Because, sorry, to elaborate on that point, because otherwise then you could like binary search over values and you could compute efficiently, like the characters, right? Which would then collapse the polynomial hierarchy.
Okay. And and what is the runtime like with the epsilon? What are the parameters that you showed of your algorithm?
What's the epsilon we chose here?
I mean, what is the runtime? You have an expression for the runtime of your algorithm, and there's some, I mean, guarantee.
I'm not sure exactly. We're playing a little fast and loose with epsilon here. The epsilon dependence is maybe something that could be better understood here. I mean, you get the runtime is bounded by I forget, it's the square or the cube of the bond dimension or something like that, right? And we can bound the bond dimension, which is immediately growing very quickly.
And okay, it's a realistic algorithm, or you have some guarantees that would like I mean,
you can guarantee the runtime without, like with the bond dimension should be, I guess, without necessarily too much. Okay, the bond dimension also will include the time for performing called SVDs, right? So that does give you like a bound on the runtime. What it doesn't tell you is if the epsilon approximation part is giving you the correct answer at the end. That's maybe the
okay, you cannot guarantee also some interval in which.
Yeah, I think we're not sure. I mean, maybe you could do some more analysis and try to cook up when that would actually give you the right value. I mean, I think I have some ideas on how to do that, but we didn't.
By the way, like what is relatively, to state the obvious, what is relatively well understood is like what impact the chopping off error for the MPS truncation or MPO, what impact that has for the overall trace distance bound. Right, that's known. I mean, that's one of the few things that's pretty well understood. Like in DMG and all these various versions, I mean, you can just, it's kind of cute to see that you can iteratively chop off things and you can still see what that means for the overall trace distance error, say, for a quantum state.
So you can also bound the error on this coefficient, on this amplitude.
I think you can.
The error propagates exponentially, maybe with.
No, I think the issue is that you do the, like, you apply one J after another, and after each application, you do the truncation.
Yeah.
And the problem is sort of the that the truncation error will get or can be amplified along the iterations. So, like, I think the bounds you mean is sort of like you apply one J and do iteratively the truncation, then you know they are that's totally correct. But along the iteration, the thing can still explode.
Possibly right. Yes, that's right. So to cut a long story short, there might be fine print that makes it complicated.
Oh, yeah, I think to make sure that it's converging, you have to.
There's the devil sitting in the detail.
Yeah, I think if you want to absolutely guarantee things are converging well, you have to take epsilon to be very, very small.
Yeah.
We sort of didn't go too far into the analysis of this because it seemed like, it was working well enough for us without doing a ton of analysis, but that is something that would maybe be interesting to get more robust results on. Okay, we don't have a ton of time, so maybe let's refrain from taking questions for a second, so I can quickly wrap up.
So that's no stress. I mean, I find it good just to hyperventilate for a second and meditate about this. It's kind of a acute application, right? Because I mean, of course, there's all these applications in quantum physics of tensor networks, obviously, but also in probabilistic modeling. There's these machine learning ideas for non-negative reals. Then here, you're not just in the audience, like we can think of function dictionaries and so on. But that's yet another interesting flavor. Quite interesting.
So like I said, we also have an implementation of this for Kafka numbers. I didn't put any of the numerics here for that, but that was also beating Sage for large N as well, which was nice. Okay, I'm gonna skip this part. If there's interest later, maybe we can talk about this. Let's see if I can just skip this through. Okay, cool. We're just gonna skip that part. This is maybe less essential for them with a little bit limited time. Okay, so let's talk about how.
Really our fault, though. I mean,
no worries. I'm happy to answer questions. Okay, so let's talk a little bit about the corresponding quantum part of this work. So, okay. We have this MPS psi G that encodes all the characters for a fixed G as you range over lambda. We just talked about creating this. It's inefficient as it should be. We don't expect this to be efficient. But what we can show is that we can compare the corresponding, actual quantum state when we normalize this efficiently on a quantum computer. The flip side being that there's a lot of different values encoded in this. So when you normalize this, everything is becoming pretty small. So it would be very difficult to just like directly read off all these amplitudes. And there's also a lot of amplitudes. So it would be pretty difficult to actually, learn all the characters from this. You could, it would just probably take a very, very large number of samples, right? So we're not necessarily going to claim that by preparing the state, you're able to compute all these characters. Again, that's a very difficult task. But okay, what can you do with this? Well, you could sample the state, right? You could just perform measurement in the computational basis. And I'll talk a little bit more about that in a second. So let me just sketch this out. I'm not going to actually go into any details on how you do this, but I'll just sketch it out for you high level. So something that's pretty important to us is the quantum Fourier transform over the symmetric group. So here you're going to start with the Hilbert space with all the basis elements labeled with elements of the group. So here G is some permutation, right? And it's going to perform the following map. So it's going to sum over all partitions lambda, so all irreps. And then you're going to get lambda ij, this vector here, with its weight being the matrix element of the irreducible representation lambda of G. So we're taking the contraction of ij here, right, to get the matrix element. So basically, this is just taking the element of the group and rewriting it where now you're indexing all the matrix elements in every irreducible representation. And I won't talk about that more here, but this is a unitary. So
Well, that's cool, but just to state the obvious, I mean, that's not the Fourier transform. It really do the, well,
It's the group Fourier transform, right?
it's the group on the Fourier transform.
yeah.
Okay, yeah. Good, cool.
And a fact from Beals from, I don't remember when, it's actually been a bit, 2
Last week.
decades or something.
Oh. No.
Boys say last week.
No, like depending on the field, there was somebody I met at QRP that he cited us that he cut the word recent from the citation because it was from September last year, so it's no longer recent. Anyway.
Well, okay, depending on your definition of recent, this is maybe recent or maybe not recent. But there is an efficient quantum circuit for this. So you can perform this efficiently on a quantum computer, which is really nice. And what we're going to do, and again, I'm not going to go into any details of this, but what you can do is you're able to perform efficiently on a quantum computer or prepare efficiently on a quantum computer a uniform superposition over everything in the conjugacy class for a specific permutation. So that's exactly what this is. C of G is going to be the conjugacy class of G. Remember that G's conjugacy class is given by its cycle type. And you're just going to take a uniform superposition over all of these. Okay, so then what are you going to do? You're just going to perform a, this should be not the inverse, but the Fourier transform. So you're going to perform the Fourier transform on this, and you'll get something that looks like this. So this is giving us the part we want, right? Because this is encoding the characters as you sum over the irreducible representations. And this part is sort of some junk.
So
Right.
because to prepare the previous slide, to prepare this this state CG, you use the inverse of that transformation, right?
No, I don't think we did, if I remember correctly.
So how would you prepare that state with the?
By controlling a bunch of permutations. There's more details in the paper about this. It's by controlling a bunch of permutations.
Okay, yeah, I know this technique, but I think it's the inverse, which would be consistent with your next slide, but yeah, never mind.
Okay, maybe I don't remember correctly, to be honest. But anyways, this is what we want. And this is some junk, but you can uncompute this junk. I mean, actually, further, for the purposes of just doing a sampling task, you actually kind of don't care about this when you have to uncompute it. But it's sort of nice that you can actually uncompute this sort of junk here and get exactly what we want, which is, some fixed reference state here, and then that, which is now encoding all the characters in the way that we want. Okay, so then what can we do in terms of sampling? Well, we can do something that we'll call row sampling here, which is exactly just preparing this state, right? And then just measure it. So when you measure this, you'll get a partition lambda with this probability. So the probability is proportional to the square of the character, right? And then we also say that you can do something we call column sampling, which is sort of the opposite of this in some sense. Where now, instead of ranging over lambda, you're fixing lambda and you can sample characters based off of the permutations, right? So you just get probabilities like this. And why do we call this or why do we call this row and column sampling? This comes again from these character tables. We look at, row sampling is going over a row, and column sampling is, going down a column. Actually, I think I might have these flipped here, but in the character table, that is. But anyways, the idea is that one's going one direction through the character table, the other one's going another direction through the character table. Again, that brings me to the last part of this. We're a little bit over time, so I'll try to speed through it, not too quickly, but. So we have these tasks that are easy to perform quantally, right? And in fact, practice, you would say there's actually going to be some error in performing these sampling tasks. And then, the standard thing we want to do based off of now there being a good bit of work in these sorts of quantum advantage experiments. If we want to argue that if you could sample these distributions classically, even approximately to some epsilon, that this would violate some complexity theory conjecture. So, a lot of those being like polynomial hierarchy.
Can I ask a question about this?
Yeah.
So I mean, if you have a sharp p-hard problem, then the sampling is automatically hard up to multiplicatively small errors, right? Can this be made robust? I mean, is it obvious that say classically sampling from the quantum distribution is like hard up to say constant error and total relation distance?
For these, we can say something about that because these are sort of structured, right? Because these have these like correctability properties.
Okay.
Which is exactly what the next like couple slides are about.
Oh, okay.
Yeah. Yeah, actually, that's
okay.
No,
If I didn't want to do it, yeah. So then
no, yeah, good point. So the idea here is that we're going to define something we call granularity. So we're going to say distribution over a finite domain is granular if basically all the probability distributions can be written as some integer times some factor over the size of the domain, something like that. So we'll call this a granular distribution. Then the idea being that, if you could learn this integer, you would then know all the probabilities, right? And that's kind of where this idea of correctability is going to come in from, because you can round integers. So, simple observation, but this lets you, using Stockmeyer, basically say that you can go from like approximately simulating to exactly computing many things. Right?
Precisely what I meant.
Yes, exactly. Yeah. So for distributions that have these properties, and this is a little informal here, there's some dependencies, but maybe look at the full text if you're interested in that part. But the idea is basically that because of this granularity property, you could correct these values right, and then just end up outputting integers that then let you compute the probabilities. Exactly. Right? That makes sense? So the idea is fairly straightforward. It's just that for this granular distribution, everything is integer values of something that we know. So then you can correct those integers. That's it.
Does this directly give you the collapse of the probability, or is the most X? I don't.
Well, okay, so we don't know if the polynomial hierarchy collapses for the things we're looking at. I'll talk about that in a second. So the idea would be, well, okay, actually, I think I maybe have an answer to your question on the next slide. Okay. Let me know if it doesn't.
Maybe I'm confused, but BPP to the NP means that you have access to an oracle which is an NP, and then you perform BPP completely. And what is this oracle? Maybe it's too technical.
Oh, what is the reduction, or what's the construction in Stockmeyer? Oh shoot, I don't remember exactly what the construction is for Stockmeyer. It's just using the NP. It is explicitly using like this as like NP, so you can like search for a specific value effectively. I think then the idea is that you just use something that can find a specific value in addition to access to the function or something like that. To be honest, I don't remember exactly how Stockmeyer goes, but it's basically saying that there's something on the third level of the polynomial hierarchy that can then exactly compute these.
So you're saying it's just a black box, well-known black box that you applied.
Yeah, pretty much.
Okay.
Yeah.
So,
yeah. I mean, I guess maybe you have to open up a small amount, but really not very much. Because the idea is, again, basically just because of this granularity, it's correctable. That's the entire thing. Like if you, right, because Stockmeyer is going to guarantee you some amount of error, or guarantee you like computing up to some amount of error, and then you can sort of correct it in this framework.
So isn't that the Stockmeyer's theorem like takes the instance as an input and the algorithm, and then produces like an approximation up to multiplicative errors?
Yeah, I mean, if I remember correctly, the idea is like pretty straightforward. It's just something about like binary searching over values. You can do this effectively with an NP oracle, because you can basically ask, like, is there something that evaluates to this?
I mean, as straightforward as it gets with an NP, but yes.
Yeah. That question.
So I think there should be something that I'm not getting here. First of all, this granular definition, the uniform distribution is granular, right? If I just put there gamma equal to 1 and set x equal to 1 for all x.
Yeah, so you may want some conditions on gamma also.
Okay, but the uniform distribution is granular, no, according to that definition. I see there.
From over what?
So over the domain.
Yeah.
Over some fixed domain.
Distribution.
Yeah, sure. Yep.
And then also a distribution that just has a single, say, atomic distribution, say that at Dirac delta, not just one guy is equal to 1 and the others are equal to 0 would also fit. That's
sure, I mean, that's fine. I mean, that's like a pretty extreme example where these things should be computed.
But in that case, it should, if I can sample from that distribution, like just take an NP problem with a quantum computer, you can sample from the output distribution, but you could never sample a solution, no? That's why in BQP you cannot solve, you cannot decide if a 3-sat formula has a solution or not, because you can prepare.
I don't think we're claiming at any point that you can actually like compute characters by doing this. If
But
that's what you're
but it seems that in this case, I would be able to compute exactly this set prime x just in BPP, no, not even with the NP oracle.
No,
We have to call too many times.
Oh. Yeah, you need the NP oracle to actually go through with this. I mean, unless this distribution has like a very small number of things, in which case you could then just sample it, right? But all the distributions I define, like the domains are pretty large, right? So you couldn't just directly do that.
Yes, yeah, exactly. So there's, yeah, I don't know. It seems like this granular definition. I'm not getting it, but yes, okay.
Well, again, really, the idea is just the fact that to compute these probabilities, it just suffices to compute in integer, and that's something that you can basically correct. That's the entire argument, basically. It's basically just like look at what Stockmeyer's does. Now use the fact that all these are integers, so then you can say that Stockmeyer, for most elements of the domain, we could do the exact value. That's, I mean, the proof is like, a paragraph or something.
Yeah,
it's actually not a very difficult observation in some sense. But it's a property that we have for our distribution, so we want to at least define it here.
Sorry, like for in the literature of random quantum circuits, this argument is used as an average case statement.
Yes.
Here also, you also consider some average over circuits. Okay.
Oh, well, okay, so we're doing something a little different, right? Because we're not averaging over a bunch of circuits, but we still want to argue something about average case hardness, which we don't necessarily know at all. I'll get to that in a second as well. So we've constructed these sampling tasks. As I'll discuss in a second, we know that they both have some nice granularity properties, well, in some cases. And we know that there's efficient quantum algorithms for sampling these things. But sort of the missing step is that then arguing that it's hard to compute most of these values. And maybe I'll get into that a little more here. So let's look at these two. We have row sampling and column sampling. We can argue that row sampling has some nice granularity under some conditions, which is true for most permutations. I'm not going to formally define what those conditions are here, but for a lot of permutations, and sort of intuitively we think of this as being having some granularity property. And then column sampling, remember, which is the probabilities are the character squared over n factorial. This is just clearly 1, right? So it has that granularity property. With efficient quantum algorithms for sampling both these, we don't know what the average case hardness of this row sampling task is. And I think that's an interesting question. I tried to think about this for a while. I wasn't really able to get anywhere. So what do you normally do when you want to prove average case hardness? Or at least the only way that I know how to prove average case hardness.
One way, no?
Yeah.
The interpolation way.
Exactly. Yeah. Reduce to like a univariate polynomial and then try to do like basically just like Lagrange interpolation using that. So then that can go from average case to like worst case hardness because you can perform interpolation to get specific values.
But isn't that all there is? I mean, if you have a gap, then you look at Nachtigall bounds, otherwise you're dead. If you want to get with average.
I have no idea. Yeah, that's the issue. I have no idea how to prove this. There are polynomial expressions for the characters. They're not particularly friendly. And also the degrees are not great, which makes these interpolation arguments not work very well. And plus the domain is not like some continuous set, right? Like say for like a permanent, which is really nice. Here the domain is now like partitions, right? Which are very discrete. It seems a lot harder to actually do like interpolation on that sort of domain. I mean, you can actually argue that you can't have like relatively simple polynomials that like interpolate through the domain also with low degree. So the things you would want to do don't seem to work. And I don't know how to prove this. This may be true, this may not be true. If it's true, it's neat and things work out here, but I don't know. If it is, it's cool.
Why can't you do the interpolation, for example, in the MPS picture? And use linearity there of the tensors for interpolation, like as in the average case hardness of PEP sampling.
I'm not sure. Maybe
That's precisely what we did there.
Yeah, exactly. Why
That
can't
was
one say
we
in this
discussed the
case?
Sharpie hardness of 2D PEPs.
Yeah.
Construction, and we look at PEPs with a R-random thingy, and then did.
I mean, I assume that it's not working because it's the wrong notion of average, but I don't have.
It's a good topic for the afternoon.
Yeah, okay, no, definitely, let's talk about that afterwards. But on the flip side, we don't think this column sampling problem is going to give us what we want. There's a quasi-polynomial time algorithm to compute these. It's just using one of the well-known like combinatorial expressions for characters, and you can show that on average this runs in quasi-polynomial time, right? So this would be unlikely because we will argue that these things are like polynomial hierarchy hard, and that would be a pretty shocking result that the polynomial hierarchy is in quasi-polynomial time. You know, that violates a lot of conjectures.
Right.
That would be a much bigger result than any of the quantum stuff in here.
We would be here if that was true.
Yeah. So okay, we don't think that this is going to give us like a quantum advantage argument. Maybe the row sampling does. We're not quite sure.
Yeah.
Let's talk more about that this afternoon.
Cool.
Okay, so that sort of brings me to the end. I did have some other stuff about the Fermionic encoding, but maybe we'll just skip that. So like I said at the start, this is what I was going to talk about. We had this tensor network algorithm for the irreducible characters. We had efficient quantum algorithm for preparing the tensor network states as well. And then this little technical lemma about arguing that our distributions, because they have these very integral properties, so you don't have to worry about the total variational distance part, and you can just sort of argue about average case complexity. But that part is also still, of course, very hard. You know, average case complexity is not an easy thing. And here are a couple of things that I think are interesting. I mean, like I've been saying, we don't know average case hardness for this row sampling problem. It'd be neat if you could prove that. And then also it'd be interesting if we get tensor network constructions or spin chain constructions for other representation theoretic quantities. In this other paper, they did have, like I said, Koska numbers, Louis Richardson's, and also something called the skewed versions of all these. Using that, we also gave a tensor network protocol for computing Koska numbers. And actually, in our Python implementation, which is on GitHub, you can find Python implementations of these skew characters and also skew Koskas as well. These are just generalizations of all these things. We didn't get Louis Richardson's. It would be interesting if you could try to construct something for that. It seems a little more difficult for maybe small technical reasons I won't get into. And it would be interesting if the other things can be encoded in spin chains. I mean, this was left as an open problem in this Krzyzewski and Prakash paper. I think that's a very nice question, which is that there's other things that are very natural in representation theory of like the symmetric group that it would be really cool if you could somehow embed them in the spin chains. And maybe not immediately obvious, but it would be really nice. And that's all I have. If there are any more questions, I can take them. Yes.
So this was all about the symmetric group.
Yep.
Are there approaches to this for like continuous groups like SUN?
Okay, so a lot of it would be harder, right? Because
so your characters are not integers then.
Well, not necessarily, but there's also like really how you would end up doing this is using some sort of duality, right? So you would use some sort of duality with a finite group. So in the example of like the general linear group, you use sure value duality to map everything to like a representation theory of the symmetric group. So like a lot of the things that appear in symmetric polynomial theory are relevant for both the representation theory of the symmetric group as well as the general linear group because of this duality. So like more generally, if you're trying to work with some sorts of continuous groups, your approach would probably be to try to argue, well, some sort of duality, at least for the representations that are like nice, and then try to use that duality with the finite group to embed all these things.
Because I know that there are like certain spin chains that people use that they can use to complete sums of characters. Those map somehow to partition functions of certain systems.
Yeah.
And, yeah, I was wondering.
Yeah, I'm not entirely sure. I have to admit that I'm a little less sure what people have done in physics to try to work with these things.
Yeah, thank you. It was very nice. On your wish list for quantum advantage, you didn't mention efficient verification. Was that on purpose?
Oh, right. Yeah, we did put that on there. I guess you would maybe want that as well. This is just sort of the structure that works for ours. Again, I think these things should not be verifiable. Like,
I mean, not black box classically verifiable.
Yeah, they should not be black box classically verifiable. I'm not
So you would have the quantum algorithm and a guarantee that whatever the quantum algorithm does is correct. And if the classical algorithm doesn't do the same as the quantum algorithm, that immediately means it's incorrect.
No, but isn't that the point? I mean, like this bit, I mean, we published about this that I mean that many of these hard sampling problems like P sampling, random circuit sampling, so they're not black box verifiable in the usual sense of like a property testing. On the classical level, if you have only access to samples, but if you have access to the quantum state, that's perfectly possible to verify. And that I would guess is that you make.
Yeah, that would be interesting. I'm not sure. I would. Yeah, I don't know. Maybe you could. That would be interesting. Yeah, that would be cool.
That would be actually, I would be surprised if that would be classically black box verifiable, and I would also be surprised if it wasn't.
Well, again, I think if it was possibly black box verifiable, you would.
Oh, that would be terrible. Yeah.
Yeah. So in your like that's the recipe, and specifically for your case, if the recipe included efficient verification, then you would know you cannot fulfill it.
Yeah, I've included classical verification. I'm not sure about the plumber. That might be interesting. We hadn't thought about that at all, but that's a good question. Yeah.
But like it would be good to have classical verification because.
Sure. That would actually be nice. Right. But I think at least the things that we're looking at here aren't going to satisfy that. But yes, you totally could wish for that. That would be a totally valid thing to wish for. I mean, I guess I have like Skyrim's like a Venn diagram in mind. Right, where he's looking for verifiability as well. This probably doesn't satisfy that. Yeah, which is definitely a limitation.
Cool. Okay.
Okay, I have two quick questions. The first is the longer, like okay.
Go ahead.
In general, like sampling can be easy while computing probability is harder than sampling, right?
I'm sorry.
Computing probability is harder than sample. There might be classes of circuits where sampling is easy while computing probability is hard.
Yeah, that could totally be true here.
And I just understanding what I know to check the knowledge, and then I ask the question, and then the computing probability with the inverse exponentially small additive error implies also sampling with the Pauli error in TV distance. And my question is, so one might want to prove hardness for computing probabilities because it's an outputting a number, and
that's exactly what we want to argue is hard here, is exactly computing these probabilities.
Yes. And this in general does not imply hardness for sampling. However,
it does in this case.
Yeah, but it does in this case. I mean, my question is, before this argument was used up to my knowledge only for random circuits, that is on average over this ensemble, like probably anti-concentration order would be.
Yeah, this is not randomly applying. So this is just okay. You run this circuit. If this is true, you would be able to argue that you couldn't basically do the same thing.
Okay, so this is worst case hardness.
You should, well, not exactly, because we want to show some sort of notion of average case hardness, right? Which is not necessarily we already know that characters actually further the square of the characters, which is what you're getting from the probabilities here, is harder than the polynomial hierarchy, right? But that's in worst case. Like there's specific families that people have constructed where these are hard to compute. You can prove that these are polynomial polynomial hierarchy hard to compute. What we need for this argument to go through is that if you could compute, let me pull the character table. So, okay, so what's been proved basically is, okay, maybe let's say like this one here, and then the family, when you extend this out to like larger numbers, like computing like this specific value is polynomial hierarchy hard. But what we would want is be able to compute almost all these values is polynomial hierarchy hard. So not the worst case, it's just saying that most of these. So you need some notion of correctability maybe on the character table, which seems kind of hard. I mean, there are the character table satisfies certain nice properties, but those properties are not super useful here because it's basically saying if you could compute, say, maybe all but one of them, you could compute the final missing one. But that's a very large percentage because these things grow exponentially large, right? So that would be saying you can compute basically everything. So we need something a little stronger than that, which is like if you can compute all, but maybe like something like inverse poly of these, then you would be able to compute any specific missing character.
Okay, so you need always some average assumption,
Yeah, so we need that like on average computing these characters is hard basically. Computing most characters in this character table is hard basically.
I see. And the error approximation, I mean, you prove hardness, okay, probably.
Well, we did prove hardness. We would like to prove hardness. We did.
Oh, okay.
We were able to get that.
But if okay, in the literature, I mean, so far this reduction are always proved in a unsatisfactory way, right? I mean, the approximation of something is never 1 over poly, right? I mean, so far the state of art in the literature, I think, is 1 over exponentially small approximation of sampling in TV distance, which is very artificial and no one would like.
Yeah, but the idea is because of these like granularity properties, we can kind of argue that this approximation part ends up not being too much of an issue for trying to argue these things.
So basically,
hard part then remaining is the average case hardness statement.
Okay. So we agree that so far the proof that use this kind of reduction, average case, yeah, it's okay. We are not yet there for a nice claim. This might be.
We didn't quite get there. Like you're missing what's probably the hardest statement to prove, which is.
I mean, not for your paper. I mean, your paper seems quite nice because you have this granularity, and this will give a meaningful hardness. While for random circuits now, the people can say you cannot have a sample with inverse exponentially small error, which is not 1 over poly, which I mean that doesn't mean anything exact simulation, exact
So
sample.
that's much easier to tackle for the granularity.
Yeah.
I remember exactly what we said. The error has to be, I think it was like something over linear and n or something like that.
Okay.
So it's, a nice-ish polynomial. But again, you still have to argue about this average case hardness part, which is even conceivably not true, right? Honestly, I don't know.
I see.
We asked some commentors and they had no idea.
And then the second question was you showed you might
They're a bit short of questions. How come?
I was reading your paper and you say that there is another algorithm that compute without the precision normalized with irregular dimension these numbers. Did you so your algorithm now is probably faster than this algorithm by Jordan that you mentioned? I mean, I didn't see a comparison. I saw only that you mentioned, but I mean,
I guess we didn't compare it to Jordan's. I mean, the irrep dimensions are actually efficiently computable, so you could actually just invert that. I mean, his thing is you have to. There's certain it doesn't efficiently compute all characters. Again, that's impossible. Well, maybe not possible, but extremely unlikely. He computed some special cases. I don't remember exactly what the special cases are here. RMPS thing is just for any family, but it's of course not going to be efficient. I don't remember exactly what regime his are efficient in, to be honest. But it's there's some regime where this is efficient. It's been since I read that paper. I don't remember exactly what the conditions are. Yeah.
Okay, thank you.
Yeah.
Okay.
Totally different direction. Maybe just for context, do you have an idea if computing these characters is practically useful for anything?
Good question.
Oh, yeah, that's
There are maybe some arguments. I would say our motivation was maybe a little more theoretical. There are maybe some arguments, some of them that I'm not super familiar with, to be honest. There's some connection to something in, I think, that's matter theory, which I'm not going to claim to have any knowledge of that, so maybe don't ask me more about that, but apparently there's some connection there. Also, in theory, these sorts of things could be useful for like kernel methods on the symmetric group. So people classically have looked at like kernel methods on the symmetric group as ways of doing like recommendations systems, basically like a permutation is sort of encoding like a preference. And so people have looked classically at running like kernels on the symmetric group. And then if you were able to evaluate certain characters, maybe you would be able to speed up some of these kernels or improve these kernels by adding some weights of certain characters or something like that. So that's one thing you can potentially do. Now, of course, that probably can't be efficient in general, so I don't know how practical any of that actually would be. But in theory, that's something you could do.
But also for this algebraic simulation, the quantizations, sometimes if you can't compute the characters, you can't do everything. So it would, like, it's the practical task of using shadows to then sort of come up with a classical surrogate of operational quantum algorithm.
The symmetric group
of groups.
Okay, because I mean, maybe similar ideas would maybe carry over to other groups, but.
Yeah.
Yeah.
I mean, okay, at the end of the day, I will admit that, you know, we probably have more of a theorist motivation going into this, but there are some reasons. I mean, also it's just, these are sort of pretty fundamental things that people have studied pretty thoroughly for a long time in math now, and sort of seem to hint at, it seems to be one of the differences about what you can do with a quantum computer is you can perform these like non-abelian Fourier analysis techniques, right? And it's interesting to ask if that actually buys you anything in the end, right? Sure.
You can have negative characters, right?
Yeah, but everything here is squares of characters because of the problem.
Exactly. So then if you can just measure the square, how does it, then you extract the square of negative?
Okay, I was sweeping this detail on the rug a little bit. The squares of characters are also very hard to compute.
Okay.
Yeah.
So everything is about computing the squares.
Everything's about computing squares, actually. Yeah. Yeah, because that's the only thing that's actually like physical with these distributions, right? Is the squares.
But then for these condensed matter applications that classify phases, would you need the square or the character itself?
Yeah, I don't know. To be honest, I mean, claim ignorance on like the condensed matter application stuff.
And sign is also hard?
Yes. Yeah, sign is also I think it's C equals P hard, if I recall correctly. So yes, it's very hard. Computing the sign is very hard. I think so. Basically, positivity is as hard as the polynomial hierarchy. Square is as hard as the polynomial hierarchy. Exactly, computing them. They're very hard to compute. So yeah, like the distributions you're measuring are in terms of. All right, here in terms of the squares of the characters, but from the complexity theoretic aspect. Like these are already, I mean, these are worst case very hard. So you would hope that the average case also is true or something like that. So that's a bit of wishful thinking, maybe.
Wonderful. We had a million questions. I think it's the perfect moment for lunch. Thanks for the wonderful talk again.